In this video, we would like to discuss the antiderivative of e to the x and look at a few associated examples. So recall that e to the x is a function that is its own derivative. So if we undo this differentiation formula, the antiderivative of e to the x is simply e to the x plus a constant. Now another form that's frequently encountered would be the antiderivative of e to a constant x. So if we think about evaluating this, and we'll do it to the side here, we could have that the integral of e to the ax, well, we could use a substitution. So let u be a to the x, so du is a dx, or equivalently 1 over a du is dx. So the ax becomes a u, and the dx becomes 1 over a du. 1 over a is a constant which pulls out front, and then we're left with the antiderivative of e to the u. So from above, the antiderivative of e to the u is e to the u, but we need to resubstitute back in. So 1 over a e to the ax plus c. So the antiderivative of e to the ax, something we can just immediately use now, is 1 over a e to the ax plus c. So these are the two new and important formulas related to antidifferentiating e to the x. Let's investigate several examples. So we'll begin with the following definite integral. So the definite integral from 0 to 1 e to the minus 4x. Now note from our previous slide, this is exactly the form of the formula that we had. So the antiderivative of e to the ax, and a could be a constant like say minus 4, is 1 over a e to the ax plus c. So by the fundamental theorem of calculus, we need an antiderivative, so minus 1/4, i.e. 1 over minus 4, e to the minus 4x, and we evaluate this thing from 0 to 1. So we have minus 1/4 hanging around. We first plug in 1, so that would give us e to the minus 4th. We put a minus sign, we plug in 0. So e to the 0 is 1, so this becomes minus 1/4, 1 over e to the 4th minus 1, and if you distribute the minus through, you would have 1/4, 1 minus 1 over e to the 4th. Alright, so another example, evaluate the given indefinite integral. Now, once again, we are in a fantastic position in Calculus 2 at this point in the semester for evaluating integrals. You either can directly compare to a formula or get there quickly through algebraic simplification. If not, our go-to method is going to be substitution. So we look for an inside function whose derivative hopefully appears outside of that function. And notice that we have this 1 over x, which can play the role of u. And what I like about that is the derivative of 1 over x is minus 1 over x squared. And we don't quite have the minus sign that we want, but this 1 over x squared dx is minus du. So let's go ahead and kind of do two things here. We have this minus sign associated with the du. We'll pull that out front. And then you also have this 2 in the denominator, which we'll pull out front as a 1/2. Then we would have just an e to the u du left over. So by doing this substitution, u equals 1 over x, all of a sudden this turns into a very reasonable antiderivative. The antiderivative of e to the u is simply e to the u, and then we need to resubstitute. So minus 1/2 e to the 1 over x plus c. Now, just for fun, as a reminder, that you can always check your work. Remember, differentiation is typically a easier process than integration. So if I want it to check, what I would need to know is what is the derivative of minus 1/2 e to the 1 over x plus c. Well, by the chain rule, we have the derivative of the outside evaluated at the inside multiplied by the derivative of the inside, and the derivative of a constant is 0. So minus a minus cancels, and what we are left with is e to the 1 over x divided by 2x squared, which is exactly the integrand that we started with. So our work is correct. One more example, the antiderivative of e to the x plus e to the x. So this one's maybe a bit more difficult, at least in terms of getting that first step. So, looking at this, we'll probably have an inclination that we're going to want to use a substitution. And the question is really, what do we use as our substitution? Now, we want to pick an inside function, and we typically think maybe the largest inside function, so something like x plus e to the x. So let's just write down what that gives us. So if u is x plus e to the x, du would be 1 plus e to the x dx. And looking at my integrand, I see I could have e to the u, but I don't have this 1 plus e to the x anywhere to kind of help form my du. So this doesn't quite look like it's going to be something that pans out. And that's perfectly reasonable. Remember, you try u substitution, you hope it's going to work, but there's never any guarantee. Now, another reminder would be that a little bit of algebra can sometimes go a long way. And going back to our properties of exponentials, and let me remind you to the side here, e to the a plus b is e to the a times e to the b. So this would be e to the x times e to the e to the x. And now I see maybe something that could be a good inside function to use for my substitution. Let's just try u equals e to the x, and to me the intuition as to why that works well is you have this kind of e to the x dx left over, and the derivative of e to the x is exactly e to the x. So when you do that small bit of algebra and see the substitution, this becomes a very reasonable integral. So it's just integral of e to the u du. So that antiderivative would be e to the u plus c, and then we once again need to resubstitute in. So that is each u needs to be replaced with an e to the x. So e to the x plus c.